predicting bond type is very easy. All you need is a periodic table. Now, we got two interesting periodic tables here. The top one kind of shows our penguins and our polar bears. The polar bears were like the animal that was hungry for the ice cream, which, if we think about it in terms of bonding and electrons, it's like the most electronegative atom. So when they're showing this big polar bear up here, that's kind of like the fluorine. The little penguins, those are the animals that maybe didn't need the ice cream, they didn't want the ice cream as much. They had lower electronegativities, and the lowest of all is our francium, down in the bottom corner. This periodic table shows electronegativity values. All elements are given a specific rating. 4.0 is the highest, so the winner is fluorine. He's got the highest electronegativity rating of all elements. And if I go to the bottom corner, francium, cesium, barium, all those big guys, number one, they want to lose electrons to obtain a full octet. And number two, the atoms are so big that the attractive forces are very weak and not likely to attract or steal other electrons. That's where you find your lowest electronegativities, in the opposite corner. And in general, all of the metals have low electronegativities. Look at group 1 and group 2, the alkaline earth. Even into the transition metals, their electronegativities are all, like 2 or less. Those are the metals that lose electrons. They're not likely to gain electrons, and that's where we deal with ionic bonding, metal, nonmetal. When it comes to covalent bonding, we know that two nonmetals will share electrons and be covalent. We just have to decide then if the bond is polar covalent or nonpolar covalent. And so again, the best example of a nonpolar covalent, super easy. Diatomics. If you have the same atom bonded to itself, like fluorine bonded to fluorine, of course they're going to share the electrons equally. They have the same electronegativity value. This would be nonpolar covalent. Best example, diatomics, the same atom bonded to itself. Now obviously, if you look on this chart, you can find some other elements that do have the same electronegativity rating. For example, carbon and sulfur are both the same, 2.6. Hydrogen and phosphorus are the same, 2.2. Well, number one, when you take a test or quiz, you're not going to have this periodic table that has all the specific electronegativity values marked in. We'll determine bond type qualitatively by knowing the trend in electronegativity on the periodic table, which means then that you won't have any on a test or quiz that are kind of ambiguous. You don't have to know that carbon and sulfur end up having the exact same electronegativity. You don't have to know that. They won't give you ones like that. They won't give you hydrogen and phosphorus. They'll give you elements that have noticeably different electronegativity values that you can just estimate by knowing the trend on the periodic table. For example, they could give me something like carbon-oxygen. And they might say, what kind of bond is this? If I look up carbon and oxygen on my periodic table, I know oxygen has a higher electronegativity. Again, I don't care that its rating is 3.4, and oh yeah, carbon is less, 2.6. I could tell you that by looking at the trend on the table. Going across, the nuclear charge increases, and so if oxygen has more protons and all the electrons are still in the second energy level, those extra protons will have a greater nuclear charge, a stronger attraction for electrons. If those electronegativities are going to be different, then this is a polar covalent bond. Or I'll abbreviate PC for polar covalent. Now the other thing they might ask you to do is this. Indicate bond polarity. That means which side of the bond is partial positive, which side of the bond is partial negative. The partial negative should always be on the element with the higher electronegativity, which I would know is oxygen, so I would indicate oxygen is partial negative, carbon is partial positive. That's it for indicate bond polarities. We indicate which end is positive and which end is negative. And so again, they could give me a whole bunch of examples. Here's a bunch of molecules, and I want to know what kind of bonds exist in these molecules. My choices: ionic. Ionic bonds should be metal bonded to nonmetal. Easiest way to pick out an ionic compound or an ionic bond. The covalents are all nonmetals. All nonmetals. And then I look for electronegativity differences. If the atoms are the same, they'll share the electrons the same. And there is no partial charge. That's what we mean by nonpolar. There's an even electron distribution. In a polar covalent, one of the atoms is different than the other, all nonmetals, but if it's different atoms, they'll have different electronegativity values. And that's where we get these partial charges. Or they're trying to show here there's a greater region of electron density. Well, since electrons are negative, that region of the molecule becomes slightly or partially negative. The ionic will totally transfer, and so then we'll have a full +1, -1 charge. Okay, so bond typing, very simple. If you see sodium chloride, you know it's ionic. Ionic. Because sodium's a metal. It's metal, non-metal, I know it's ionic. If you skip to 3, fluorine, fluorine, we just mentioned it. It's the same non-metal bonded to himself. That is your non-polar covalent. But if you have something like 2, water, it's 2 non-metals and they're different non-metals. That means they'll have different electronegativities. Polar covalent. Now in the next video we're going to start looking at drawing pictures of molecules. Here's kind of what water looks like. Water has the oxygen and 2 little hydrogens kind of coming off the bottom. We have 2 of the same bond. The bond is between oxygen and hydrogen. And so really I just want to know what kind of bond is that between oxygen and hydrogen. And if I look at their position on a periodic table, I definitely know that oxygen has a higher electronegativity. So if they ask, the oxygen end of the bond is slightly negative and the hydrogen end is slightly positive. And it would be the same thing with this other bond. The oxygen is negative, slightly or partially negative. The hydrogen is partially positive. The electrons in this bond are drawn toward oxygen. He has the higher electronegativity. Same situation with CH4. 2 nonmetals, but they're different. Polar covalent. This one has the carbon in the center, and then it's got 4 little hydrogens around the outside. And so again, there are 4 bonds. They're all the same. They're all bonds between carbon and hydrogen. Now, the electronegativity difference might not be quite as extreme as in water, because even between oxygen and carbon, oxygen has a higher electronegativity. But between carbon and hydrogen, carbon still has a higher electronegativity than the hydrogen. It's a polar covalent bond. The carbon will be slightly negative, and all of these hydrogens are partially positive. Partially positive. In all of the bonds, the electrons are drawn toward carbon because of his higher electronegativity. Polar covalent bonds. There are 4 of them. And so again, if you look at 5, phosphorus and oxygen, what kind of bond exists between phosphorus and oxygen? I don't care so much that it's P2O5. If I look at a periodic table, I know that oxygen has a higher electronegativity. It's a smaller atom with greater nuclear charge, greater attractive forces. This is a polar covalent bond. And if they asked, the oxygen would be partially negative, with the phosphorus partially positive. 6 and 7, easy. Calcium is a metal, ionic. Potassium is a metal, ionic. Hydrogen and fluorine are both nonmetals. It's covalent. They're different nonmetals. It's polar covalent. With the electrons closer to fluorine, fluorine will be partial negative, hydrogen partial positive, because of fluorine's higher electronegativity.